Take it away.
Thank you. So my name is Moritz Jodeit, and this talk will be about USB security, especially on the security of USB device drivers and other kernel code. And we'll start with a small introduction to USB in general. Then I will give some motivation why we should care about vulnerabilities in USB device drivers. We'll look at some attack surface which the USB device drivers provide compared to other device drivers. And then the main part of the talk starts, which is various approaches on how to actually find new vulnerabilities inside USB device drivers and also other code of an operating system. We'll show various approaches using hardware and also our approach using an emulated environment, which is our current Fuzzing Framework. So I'll show a little bit of that implementation. And finally, I'll talk a little bit about crash analysis. So how you actually can reproduce crashes and what problems we encountered. And last but not least, we will list some of the findings we found during our evaluation. So who am I? My name is Moritz Jodeit. I'm a private security researcher and like to do bug hunting. For a living, I'm a pen tester at Enrans AG in Germany, and I live in Hamburg. Actually, the talk was supposed to be given by Martin Jons and myself, but he's currently moving and he didn't make it to the conference, so I'm doing the talk alone. So first of all, some small USB introduction. So probably everybody knows about USB. So it's a universal serial bus, which can be used for lots of different devices. It provides various speed modes, which makes it applicable to various devices. And the latest specification is actually USB 3.0, which was released around 1 year ago. But all the devices you currently find on the market are still USB 2.0 devices. There's even a wireless extension for USB. It's called CW-USB, which is really an extension, so you can keep all your device drivers and devices and just use the wireless link. So I will talk a little bit about that later on. So the USB architecture mainly consists, or basically consists of a single host and multiple devices. And it's important to know that the host is the only controlling instance on the bus. So a device can't just send some data to the host, but only if the host requests it to do so. So if a device wants to send data, the host continuously mainly polls all devices on the bus and asks them if they want to communicate. And if a device wants to send some data, it just responds and then has the possibility to send the data to the host. Then we have the process of enumeration, which starts when a new device is attached to the bus. This is the process where the host learns about the device. So they exchange various information. The host needs to know those information to make the communication work and to find a device driver or multiple device drivers. And the enumeration basically exchanges so-called descriptors, which are just some basic blocks of information, which, for example, contain vendor IDs, product IDs, various packet sizes. And there are even string descriptors, which are provided by devices which contain human-readable descriptions of the device. And in USB, we have various concepts like endpoints, pipes, interfaces, and configurations, which are best explained using some graphic. So in this case, we have a single USB host connected to a single USB device. And all the communication between the host and the device travels through so-called pipes. So each of the arrow represents a pipe in this case. And each pipe is connected to an endpoint on the USB device. So if a USB device wants to send data or receive data, it has to do it through an endpoint. each USB device must provide at least one pipe, which is called the default control pipe. And that's the pipe where actually the descriptors are exchanged and where the enumeration happens. Of course, USB devices can provide more pipes. So in this case, there are some more. And multiple pipes can be grouped into interfaces, where an interface just provides a single functionality of a device. So one interface might provide a mass storage device or mass storage interface, and another interface might provide, for example, keyboard functionality or mouse. And on the host side, each interface is handled by a single device driver. So in the usual case of a USB thumb drive, you have a single client driver or client software on the host. But USB devices with multiple interfaces are possible, of course. So what is the motivation behind going into the research of USB vulnerabilities? So it's a physical attack vector. So one thing you can do is, of course, social engineering attacks. So you can provide or you can build a malicious USB device and just place some of them in front of some company you want to attack. And then suddenly some employee will pick up one of those devices and maybe attach it to their workstation, and thus you could gain access to their internal network. Another attack vector is, of course, to gain access to locked workstations. So if you're inside some company or some conference and you want to get access to some computer system, you can use your malicious USB device, attach it to such a system, and gain access. Many people I've talked to thought that USB enumeration would not happen while a workstation or Windows workstation is locked, but that's not true. So even if your workstation is locked and you plug in a USB device, enumeration happens and device drivers are loaded and the device communicates with the host. So later on, I will show you some vulnerabilities we found during our evaluation. And all those vulnerabilities were triggered even though the Windows workstation was locked. Another motivation was the digital voting pen. That was actually the reason we started all this research. So last year in Hamburg, there was supposed the election, and the election should be done using the digital voting pen, which is some pen you can use to make your crosses, which is then passed to the election supervisor, which in turn attaches this to a USB docking station, which then transfers the votes to the workstation, where all the votes are stored. So one motivation is you could eventually just modify such a device or replace it. And when it is attached to the system, it could own your system, and you could do vote fraud with it, or election fraud. And of course, as I said, the wireless USB standard is just an extension. So all the vulnerabilities we find with usual USB devices can, of course, then be reused if or when the wireless USB devices gain more widespread use. And of course, there are many places where unprotected USB ports are provided. So even on airplanes, there are some cases where you have a USB port in front of your seat. And there are many examples more. So what are some of the known attacks and some of the attacks we thought about? Something which is always in the media is data leakage. So someone just loses their thumb drive with critical information, or someone just walks into a building and copies data onto his USB stick and steals data this way. Another example is autorun malware. So there is some kind of malware like the configure worm which spreads using the Windows autorun functionality. So you can disable this functionality for thumb drives, but even if you disable it for thumb drives and it's still enabled for CD-ROM drives, you can still exploit it in a social engineering attack. You can use those U3 flash drives, which basically provides two interfaces. So it provides a mass storage interface and a CD-ROM interface. And it's usually used to start up all your Windows applications from the flash drive without installing them. And usually, when you attach it, the CD-ROM partition contains an autorun.inf file, which just launches this U3 Windows application. But you can actually modify the firmware of those devices to run any application you want. So even in this case, you could use it for social engineering attacks to start any application you want. Another attack we thought about. Yeah. The question was if the attack still works if autorun is disabled. You can disable autorun for various devices. So you can disable it completely, but you can also only disable it for mass storage devices like USB thumb drives. And if it's enabled for CD-ROM drives, then this attack works. So you can still plug in this USB stick and it will start any application. Another attack we thought about is a malicious USB mouse keyboard device. So we thought about building some device looking like a USB thumb drive, but which would provide three different interfaces. So it would provide a single mass storage interface, which would get mounted in Windows the usual way. And it would additionally provide two interfaces, or one, like a mouse or keyboard interface, which would not immediately get detected by the host. So you would plug in such a device to a workstation. The mass storage interface would get detected, and the partition would be mounted. And finally, after some defined period of time, maybe, the mouse and keyboard interface would get detected and would automatically control your workstation to run some application lying on the partition. So this way, you could, even if autorun functionality is disabled, you only have to get this device to some workstation, and maybe you have to take care that nobody is in front of it, and then you can automatically run malware from the attached device. And finally, of course, there are implementation bugs, potential implementation bugs in the USB stacks and device drivers of operating systems. And that's actually what this talk will focus on. Compared to other device drivers, the attack surface is a little bit larger. So in this case, we have a really simplified overview of an operating system. So at the bottom, we have the electrical layer where all the data from a USB device comes in. And the first thing which happens if you attach a USB device is the USB stack talks to the device and performs the device enumeration. So that's the first part where bugs might lie, and you could eventually trigger those. So after the enumeration completed, a single device driver is selected, so that's the next part. The device driver talks to the device, and even in the device driver, you might find bugs. But compared to other protocols, those device drivers don't implement all the functionality themselves. So in the case, for example, of a USB mass storage device, you are talking a limited set of SCSI over USB, and for this purpose, it's using the SCSI subsystem of the operating system. And also, you provide partition tables and the code from the operating system to read those partition tables and to do the file system thing are also some other kernel subsystems, which indirectly get in contact with communication from a potentially malicious device. So you might even find bugs in those kernel subsystems. And it doesn't stop there, because there are even user mode applications talking to USB devices. So one example is for the Apple iTunes software talking to an attached iPod. So in that case, you attach the device. The stack is handling the device and loads the mass storage device driver. The mass storage device driver is detected by the operating system, and if you install the iTunes software, it installs iTunes service binary in user mode, which is running a system and which sole purpose is just to detect the attachment of a new iPod. So that's one point where communication hits some device, some service in user mode. And if an iPod was detected, it automatically launches the iTunes application, which in turn just communicates with the device as well. So there are lots of places where we might find bugs. And yeah, actually, how can we find bugs? So we mainly used fuzzing techniques. You can, of course, just use any auditing technique you can think about. So for example, for Linux-based things, you can just audit the source code. But we concentrated on fuzzing. And in the following, I'll show you the approaches we thought about and which we implemented most of them. And we'll start with a complete hardware-based fuzzer. Then I'll show you our hardware-aided approach, where we combine the benefits of implementing the fuzzing part in software, but which is still hardware. And finally, I'll show you how fuzzing in emulated environments can be used to find new bugs. And finally, I'll talk a little bit about USB over IP. So a complete hardware fuzzer has a big benefit that you have no indirect layer or middle layer which could influence your results, as we will see later. So you have direct connection to your target and just attach it, and the only thing you need to have is an open USB port. So you can even use it to fuzz embedded devices. The big disadvantage of the hardware solution is the limited control over your fuzzing target. So if your target stops responding, you only have the possibility to physically reset it. So in one case, we tried to fuzz Windows XP using a hardware fuzzer, and we continuously attached the device and removed it and attached it again. And we modified the data exchanged on endpoint 0. And suddenly, after some attachments, Windows would stop enumerating new devices. So the only possibility to get back the USB functionality was actually to physically reset the system, which is not very practical for a long fuzzing run. And of course, if you have a complete hardware-based fuzzer, you have to write firmware and flash the firmware on the device. And for development purposes, it's not that practical. So there are more practical solutions. So to overcome this limitation with the inflexible development, we created a hardware, what we call a hardware-aided software solution. So we still use hardware to connect to the target system, but we implement our fuzzing engine completely in software. So for this purpose, we used the Linux USB Gadget API framework, which is part of the Linux kernel. It's a framework which allows you to program your USB devices. So it's, for example, used in Linux-based mobile phones. And it consists of two kinds of drivers, which are, first of all, the peripheral controller drivers, which is basically the contrast to the host controller drivers on the host. And we have gadget drivers, which provides actual functionality of a device. So it already ships with some gadget drivers like Ethernet driver, mass storage, serial, and MIDI driver, which all are full implementations of their devices. So with the Ethernet gadget driver, you can implement a fully functional USB Ethernet device. In addition to that, we have also the Gadget FS driver, which doesn't provide any functionality itself, but just gives you the possibility to write your own driver in user mode. So all those other drivers are kernel mode drivers. And this one just provides some user mode bindings, so you can write your own in user mode, which is really practical. The framework provides or supports multiple controllers. Most of them are some controllers for embedded systems. We actually used the NetChip NET2280, which was basically chosen because it provides a PCI evaluation board, which allowed us to use our current workstation to perform the fuzzing and don't spend some time on developing embedded systems. So that's how it actually looked like. So we have a small Circus board, which just is connected to our NET2280 card, which in turn is, in this case, connected to the fuzzing target, which is a Mac Mini in this case. Yeah, some disadvantages of that approach is actually while fuzzing, our fuzzing workstation encountered some deadlocks. So it seems, because we just attached and reattached really fast, and it seems the framework isn't supposed for fuzzing, so it's mainly used for developing actual working devices. So we did a lot of fun stuff, and then sometimes our workstation locked. And of course, we still have the problem of bad target control, because we are still using some hardware to fuzz some other physical workstation. Yeah, but it's really useful, actually, to build your final exploit. So once you found some vulnerabilities and you want to implement your final implementation of it, you can you can write you can write your exploit using that framework. So you don't have to implement some firmware, but you can just write your exploit in user mode, even using the gadgetfs driver, and that's really easy using that framework. So our next step was to implement fuzzing in emulated environments. So we had the problem of the bad target control, so we couldn't fuzz Windows XP on endpoint 0 because it always stopped. So we thought about fuzzing in emulated environments. So we basically either emulated a complete device in software and attached it to a virtual machine, or we used a physical device and just send the data from the physical device to the virtual machine in order to fuzz it. So the really good thing about virtual environments are virtual machine snapshots. So if your target doesn't respond anymore, you just revert the snapshot and continue fuzzing. And you can also use virtual machine snapshots for actually reproducing found crashes. So once you found a crash, you just revert to the time before your attachment, and you just reattach your malicious device or your modified device, and thus can reproduce crashes most of the time. Of course, we are in user mode, so we can use high-level languages like Python or Ruby. And there are actually some interesting side effects if you don't pay a little bit attention of what you are actually fuzzing. So there are some bugs in virtualization solutions like VMware. So in this case, we try to emulate a mouse device and try to attach it to a Windows XP system inside VMware, and it just segfaulted on us. So it just said unexpected signal 11. So you have to take a little bit of care that you don't trigger crashes inside your virtualization solution you are using for the fuzzing. But despite that fact, it works really well. Yeah, the last approach, which we actually didn't implement ourselves, is USB over IP. So there are multiple USB over IP bridges on the market, which allow you to attach your USB device over the IP network at a remote workstation. And that's really cool for fuzzing, because all your USB packets are actually encapsulated in IP packets, so you can basically use existing fuzzers and fuzzing frameworks for that, and you don't have to write anything yourself. And you can also use it as a USB hardware sniffer. So if you're just interested in the communication between a host and a device, you can just take a look at the communication, and this is used as a hardware sniffer. The bad thing about it is that all bridges we know of require software to be installed on the host side. So at the device side, you always get this hardware device where you can plug in your USB device, but on the host, you have to install some filter driver or some other software which receives the IP packets and decapsulates them. There are multiple solutions. So for example, you have a solution which runs on Linux, which runs on Windows and OS X, but it's not that cool. So we wanted mainly a device which you can use for fuzzing any device you encounter. And we are actually currently planning our own USB IP USB bridge, so that you have hardware on the left, hardware on the right, and just tunnel the USB packets through IP. But that's really work in progress and not really done yet. So that were the approaches. So if you're fuzzing USB, you have to decide what to basically fuzz. So you can do it with generation-based fuzzing or mutation-based fuzzing. So complete generation-based fuzzing is really time-consuming. So in that case, you generate all your data structures from scratch. So in the case of USB, that basically means you have to write your own gadget driver. You have to implement all the device functionality yourself if you want to get really good code coverage and cover all the functionality. On the other hand, you can also do mutation-based fuzzing, which is just you take the stream of packets exchanged from a real physical device, and you modify the communication of that device. So you don't have to know anything about the exchange protocols, and you can really quickly get some first results. So that's what we call USB man-in-the-middle fuzzing. And we decided to, first of all, go with a mutation-based fuzzing approach, and that's what we implemented. Actually, the generation-based fuzzing can be used for some simple cases. So for example, you could think about just enumerating through all the vendor and product IDs, and you could actually fuzz the first part of the enumeration, which exchanges some of the default descriptors. But after a time, each device behaves according to its own specifications, so you can't do general fuzzing above the enumeration process. So that's what we implemented. We implemented fuzzing, or the USB man-in-the-middle fuzzing, in emulated environments. And we implemented that as a patch to QEMU. All the fuzzing logic itself was implemented externally as a Python library. And that allowed us to easily write our own custom fuzzers based on that framework. It was basically composed of 3 components. So on the left, we have the receiving component, which sole purpose was to just gather all the packets from a physical USB device. The packets were forwarded to the processing component, which passed the packets to our fuzzing framework in user mode and just allowed registered fuzzers to modify the packets. The packets were passed back to the processing component, and finally handed off to the device emulation component, which just has a responsibility to pass the packets to the final target host, which was a virtual machine in our case. But we use this separation into those components because if we would decide to skip the fuzzing in emulated environments and would like to fuzz using some hardware, we could just replace the device emulation component and actually connect it to some hardware device, like the NET2280 we saw before. So this is how our fuzzing framework looks like. So at the top, we have a physical USB device, which is attached to our workstation. So it's handled by the host controller, and then the USB device file system passes the communication to user mode. In user mode, QEMU receives the USB communication from the real physical device. And then our receiving component, which is implemented into QEMU, just gets the packet and passes them to the processing component, which is a separate Python library. So the communication to the processing component works using named pipes. And then each registered USB fuzzer gets the chance to modify those packets. And after that, all those packets are passed back inside QEMU to our device emulation component, which just passes the packets back to the target virtual machine. Actually, that worked really well. but it still was not really satisfying because we were still restricted to QEMU. And we also had to patch QEMU, and we don't like maintaining patches. So we thought about some other solution or some modification to our approach. So that's what we are currently doing. So we thought about each virtualization solution is using the USB device file system to talk to physical devices. So even QEMU, VMware, VirtualBox, they are all using the device file system. So what we are doing now, we attach to the process, which can be VMware or QEMU, and we just intercept all the relevant syscalls using ptrace, which access the, the USB device file system. So that way, we get access to the data from a USB device before the virtualization can see it. So we modify the packets and then just pass them off to the virtualization. As I said, it's a universal solution, and it can be used for QEMU, VMware, and VirtualBox, and basically everything which runs on Linux. And we don't have to patch anymore. One other aspect you have to think about is how you actually want to attach and detach your devices automatically. So you don't want to do it by hand, because that gets boring after some time. Using QEMU, you can use those monitor commands, USB add and USB del, which just takes a physically attached device with a given vendor and product ID and attaches and detaches to the virtual machine. Using VMware, we couldn't find an API in the Wix API which actually would attach or detach a USB device. But what you can do is you can just revert to an old snapshot or start and stop the target virtual machine, which triggers a reattachment of all USB devices which were attached before. So you can use that to actually attach and detach devices. So that's how our current fuzzer looks like. In this case, we are using VMware and are fuzzing Windows Vista with the latest service pack. And I don't know if you can see it, but we fuzzed the first 10 packets, or some of them, which triggered a blue screen in this case. And yeah, after each attachment, we are checking if our target VM is still alive. In this case, it wasn't, so fuzzing stopped, and we can analyze the crash. This was actually one of the crashes I will show you later, which was triggered by attaching and detaching a Microsoft VX1000 webcam. Yeah. So crash analysis. There are two approaches we took in trying to reproduce a crash. So getting the blue screen is the first thing, but then you of course want to reproduce the crash so you can analyze what happened and so on. And one thing we did was we just look at the packets or at the packet number we are modifying, and we store the bytes we modified in some space, and then we reattach the physical device and just reapply our modifications based on the packet numbers we see. That works really well if your crash happens after only maybe 10 packets, but it doesn't work so well if you're attaching a device and after hundreds of packets your host crashes. That's because USB devices don't always send the packets in the same order, and for that case, we thought about just replaying the whole communication of a device. That actually works really well for simple protocols. So, for example, we used a HIT device, a mouse, just let it attach, move the mouse a little bit around, and record all the communication, and we could actually replay that. So it would attach again without the device attached, and the mouse would move just magically. But it actually breaks with mass storage devices. So the enumeration, if you record a complete attachment of a mass storage device and you replay it, the enumeration happens, so the device is detected, but then finally it breaks. So it's not that easy, so you might modify some of the packets before you can completely replay them. So that was actually one of the parts where further research is needed, because some of the vulnerabilities we found, which I'll show you in a minute, were actually not reproducible using both of these approaches. So to actually test our fuzzers, we did some small evaluation, which was really basic. So at first, we only did really simple dump fuzzing. So we only used physical devices and just flipped some bytes in the communication, just randomly. And our main target was an Apple iPod. So as I explained already, it has contact with many different parts of an operating system, so it was a good test candidate for evaluation. In addition, we used some other devices we had lying around. So what we found, using the Apple iPod, it was just connected to a Windows XP system and continuously attached and detached. And the first thing we found was a double free of kernel pool memory in the USB store.this driver, which is actually the USB class driver for mass storage devices. Another thing we found was some kind of kernel pool memory corruption in the disk.this driver, which actually happened while reading the partition table. So that's one case where you don't, at the first hand, think that it might be related to USB. And additionally, we also crashed the iPod service exe, but just with a lame null pointer deref. But that also shows that it could be possible to attack software even running in user mode using malicious USB devices. Yeah. Then we also did some light fuzzing using the VX1000 webcam. We tried to fuzz using this camera on Ubuntu, which resulted in null pointer deref in the webcam driver. We also fuzzed a little bit on Windows Vista, which also resulted in a null pointer deref in the VX1000 this driver, which is the webcam driver coming with this webcam. And finally, we used various mass storage devices, which resulted, or one of those resulted in another null pointer deref on Windows Vista, actually inside the USB hub driver, which drives the USB hub. And we had one crash where probably a function pointer was set to null and then called, but actually that was one of the crashes we couldn't reproduce using either of the approaches I already mentioned. So that were our findings. So in conclusion, we can say that fuzzing in emulated environments seems like the right approach. So it really simplifies fuzzing. The reproduction, as already said, can be hard sometimes. So there further research is, of course, needed. And there's, of course, potential for more vulnerabilities to be discovered. So our fuzzing was really only dump bit flipping. So you can think about doing some more intelligent fuzzing. And of course, we can also look at third-party drivers, which might have a lower quality eventually. So, any questions? By the way, the fuzzer will be published at some point in time, but it's currently still a little bit of proof of concept. So, but if it's ready, it will be published. So if you're interested, you can just drop me a line and I'll tell you where and when. Yes?
So the vulnerabilities you found so far.
Sorry, may I interrupt? I'd like to get this onto the recording. Sure.
So, of the vulnerabilities you've discovered so far, any of them exploitable at the moment, or have you investigated?
We didn't really investigate, but the ones, the double free of kernel pool memory and the other kernel pool memory corruption might be exploitable, but we didn't really investigate the exploitability.
Yeah, thanks. Nice talk. And did you compare the performance of your QEMU-based patch approach and the syscall hooking approach?
No, not really. But it doesn't seem, yeah, the impression is not that it's really slower than the other one. So no really performance hit you might expect.
Any more questions? Wait.
Yep.
Hi, have you tried VMware's record replay functionality?
Nope.
Because that allows you to completely replay an instruction stream and absolutely everything in VMware.
Okay. So
But
it's not,
I don't know how it works with external devices or anything.
So it's not related to USB especially, but it just replays.
You can rewind and then restart again, and everything is replayed in exactly the same order, and the same interrupts, and everything occurs exactly the same as it did previously.
Okay.
So
That might be a nice solution to actually trying to reproduce a found crash. So I will take a look into that. Thanks.
Questions? Well, if there's any more questions, how long will you be here tomorrow, including
Tomorrow, yeah.
things? And weekend, maybe?
Yeah, of course. Just
Okay.
come to me and ask.
So, yes, please direct your questions to him. Right now, I would like to wrap it up because this is the time for the break. Please be back after the break. And the best place to sit up is in front of here, so please move up. Thank you.